You all right, Doug?
Yeah, I don't know. Runny nose for some reason, but don't know why.
Pollen. Spring is starting to do its thing.
That's right. It's in the air.
I know. I've been out fighting the blackberry bushes up behind my house for the last few days. I think I'm winning, but it's hard to tell. Usually it's a draw. Doug, if you want to go ahead and get us kicked off.
All right. Welcome, everyone, to this month's 7x24 Northwest Chapter meeting. We are thinking about having a September meeting in person. Have not made a final decision yet, but we certainly welcome your input, either by email or perhaps after this meeting we can hang around a few minutes if people want to express their opinions one way or the other. It would be in September, so it's a few months yet. And we're still validating a place to meet, so that part hasn't been resolved yet. But that's one item. Another item, we have started a scholarship meeting or a scholarship committee, and the first series of meetings for those are coming up soon. If there is residual interest on joining a scholarship committee, let Jim know, and we'll take it from there. Apparently the National is meeting soon. I don't remember the dates. Bill, do you remember that?
Not without looking it up right off the top of my head. It was
June something or other, but that's something you can keep your eye open for.
June 13th.
13th, and I think those are face-to-face meetings also. Is that who knows one way or the other?
I believe that is. Give me just a half a second here and I'll find it. I wanted to say they were doing it in San Antonio this year.
That sounds right.
Yes, San Antonio is correct, and it is face-to-face.
June 13th through the 16th at the JW Marriott San Antonio Hill Country.
Nice. All right. So is Anthony with us and ready to go?
Yes, it's with us. And do you have the intro there, Doug?
I don't have the full intro. It's Anthony with the National Accounts Manager with Mitsubishi Electric Power Products, and he's talking about silicon carbide and the power conductor technology associated with that.
So let me just add to that. We'd like to thank our chapter member, CPSI, for arranging Anthony Pinkney's presentation today. And here to give a little bit more introduction is Robert Walker from CPSI.
Thanks, guys. I just wanted to provide you a little intro. You know, we worked with CPSI, we worked with Mitsubishi for a couple decades now. Myself personally, both at CPSI and other places I've worked. And I know there's a few people in my career that I look up to and I know are knowledgeable, humble, and very helpful. And Anthony Pinkney is one of those people. So I'm very pleased that he agreed to do this for us. So with that, I'm leaving it to Anthony.
Yes, thank you very much, Robert. And before I take the screen over, I would like to say that last week I was in Kansas City Thursday and Friday at the 7x24 Midwest meeting. And it was face-to-face, and they had a record attendance. And I thought it was very well done. So one day was a golf outing, and the second day was the conference. So with that being said, let me see if I can share my screen here. Yep. How are we doing? Does that
You're good to go, Anthony.
full screen? Okay, thank you.
Thank you.
Okay, there are 4 parts to today's story. Part 1, what exactly, and the title of the presentation is The Silicon Carbide Revolution. Well, what exactly is the revolution? Part 2, where's the battleground? Part 3, who's funding this revolution, and part 4, 2 intimate stories from inside the revolution. My background, I'm a New York City boy, born, raised, educated there. I'm a double E from Manhattan College, electrical electronics engineering. 35 years in the industry, sales, product management, marketing, company owner, had my own company, author, speaker, and on the side, I represented the U.S. Playing rugby in 10 countries. And I want to welcome you to the revolution. Some technological revolutions are flashy. You know them when you see them, like your phone. How about that? Your phone recognizes you. You've got augmented reality. There are 3D screens. Your phone is your bank, and coming soon to your neighborhood on your phone, you're going to have holograms. Very flashy. How about the electric car? Bullet trains, supersonic airplanes, right? These products are all faster. They're all more efficient, environmentally friendly. They all embellish cost, size, and weight reductions, all from the revolution that they're in. Well, on the other hand, some technological revolutions are very subtle, like the behind-the-scenes revolution that's going on in power electronics. These devices here that you see on the screen, semiconductors, transistors, they're converters, they're inverters, they're changing current. Advances to these devices provide us with more efficient ways to manipulate, regulate, and convert electricity from one form to another. This is the real revolution. I'm going to speak to what these products are doing to our everyday life, to our business life, and we might only see the flashy part of what exactly is happening. So, power electronics devices at work in the smart grid. Now, the smart grid looks very complex, but over here on the left, we have power generation. That could be nuclear, it could be wind, it could be solar. All the way on the other end of the stick over here, we have consumption. We're consuming electricity. But if you notice, between the left side generation and the right side consumption, we're constantly converting energy from AC to DC, from DC to DC, from DC to AC. This is the story of what's going on inside this power grid. Currently, 60% of generated electric power passes through power electronics devices between the generation and the use. So we're getting our hands on power one way or another. Now, with these devices, to conduct current, to power something up, you have to load it with a material, right? So for the past 60 years, the material used to conduct electricity inside these devices has been silicon. We all know silicon. We all know there's a Silicon Valley, there's a Silicon Gulch, right? Well, as a material, we as engineers have pushed silicon electronics or electrons to their limits. It's time for a revolution, and it's happening now. As with all revolutions, someone or something is going to make an exit, right? Well, you can say goodbye to silicon. Good old number 14 on the periodic table is on its way out. And I'm going to talk about that and tell you why right now. How did this happen? Well, we're going to have to go back to Physics 101 to understand what we've been doing for 60 years and why we're changing. And it all has to do with the conduction of electricity, which starts with an atom. There are all different kinds of atoms out there, but they all have in the center a positively charged nucleus. And then there are orbits of electrons circling around this nucleus. These electrons are negatively charged, and positives and negatives attract, and so the atom stays together and it moves around in life, right? So these are how atoms are set up. Every atom is positive. The nucleus is positive, and the electrons are negative, right? But here's what I want to focus on right now, because my whole story is going to be about this. Electrons can only exist in their electron bands, these electron bands. Between each band, there's what's called a band gap, right? Very, very cleverly named, a band gap that separate the electron bands. These are no man's land. Electrons can't live in these gaps. And my whole story is going to be about the gap. So what exactly is electricity? Some of you out there might not know. It's the movement of charged electrons, these negatively charged electrons, from one atom to another. Now, these are silicon atoms, right? I said we've been using them for 60 years. So from one atom to another, we have this flow of negatively charged electrons, right? The electrons are not tied to a particular atom. They're on the move in what's called the conduction band. And that's what's going to happen in all of those devices I showed you. We're going to conduct electricity. So here's another way to look at it. These are all silicon atoms here on the middle of the page. All of these silicon atoms have 4 electrons in its outer band. Now, we need to move these electrons from the silicon atom into the conduction band in order to have electricity flow, right? And it's got to cross that band gap. It's a band gap, so in no man's land, we're going to have to find a way to get this electron into this conduction band. And there are 4 electrons in the outer band. Now, the outer band here is called the valence band, all right? You'll see it on more of my slides. The valence band. We're going to pick on the electrons in the outermost band because if positives and negatives attract, well, the least amount of attraction will be from that nucleus to the outermost shell, the valence band. So these are the guys we're going to pick on. So here's the goal, to get an electron from the valence band into the conduction band. That's the task at hand. Here's another schematic where on the bottom you see the y-axis here is it's energy, right? And so we have a valence band of available electrons. These are silicon. If we're looking at silicon atoms, these are the available electrons that we need to move into the conduction band, right? So we need energy to get these electrons across this forbidden zone, this band gap. Not all band gaps are the same. That's what this story is all about. We're going to look at a silicon band gap, and then we're going to look at a silicon carbide band gap. So not all band gaps are the same. So here's our job, to get those electrons moving. Now, this is a very interesting slide. You know why? Because it describes all matter out there. Oh, there's all kinds of different atoms. Some atoms are good at conducting electricity, some are not, right? So let's take a look at what we're going to be looking for in life here and what has happened in the last 60 years. I'm going to start with metals. Now, metals as atoms, they have no band gap. There's no gap between the valence band, the available electrons to move into the electric conduction band. There's no gap. So if there's no gap, that means that electrons can just move back and forth all the time. We don't have to find a way to get them across the gap. Now, a good example of a metal is copper. So that's why copper is such a good conductor of electricity. There's no band gap to get into the conduction band. It's flowing all the time. So we don't want to use metals for what we need to do to conduct electricity. Let's go to the other end over here to the insulators. Now, you can see that the insulator materials, atoms, they have such a wide band gap here that no matter how smart we are, we can't figure out how to get electrons into the conduction band. These materials, these atoms will never conduct electricity. This is glass or plastic, right? We're not interested in them. What we're interested in is a material. Now, the material itself is called a semiconductor. And up until, including today, we're using silicon. Silicon is a semiconductor. It's got a band gap that's just right. And smart guys that we are, engineers, we can make this band gap wider to stop the flow of electricity or make it narrower to facilitate the flow of electricity. So this is what we're looking for, a semiconductor. And that's where the term comes from, semiconductor. So now we know what we need to do. We're going to use silicon atoms. The silicon atoms are semiconductors, right? A semiconductor material. How do we get the atoms across that band gap into the conduction band? Okay, again, we're going to need energy to bump these electrons into the conduction band. And the energy can be a voltage, which is what we will do with our semiconductor devices using, power electronic devices. Then there's solar power. I'll address this very briefly later. And then there's heat. You can use one of these forms of energy to bump into the conduction band. So for the last 60 years, in order to get a silicon electron from the valence band to the conduction band, we needed to hit it with 1.1 electron volts of energy. Then we could get it across the band, right? And it's been working and working and working. But with silicon, I'm giving you a look into the future here. With silicon carbide, this band gap is going to be 3 times wider. And it's going to take 3.25 electron volts for us to get that electron into the conduction band and conduct electricity. But you might say, well, how could this be good for us if you need more energy to do this? Well, wait till you see what these electrons do when they get into the conduction band. Is going to allow us to do things we were never able to do before with power electronics. You're going to see those flashy technological advances in front of your eyes. So silicon carbide is a wide band gap material. Its band gap is 3 times wider than silicon. So another view of this is that we're going to bump this atom or this electron from the atom, the silicon atom, into the conduction band, and with 3.25 electron volts. I'm restating myself, but it's the band gap that determines how a material's electrons behave as electric current. We're going to change electric current by changing the band gap. Not going to go into the physics of the whole thing, but we go through that, we get the wider band gap material, and here's what happens. Because it can get across the wider band gap, silicon carbide can sustain 10 times higher voltages than silicon and 10 times the breakdown voltage if you happen to be designing IGBTs or transistors or these power electronics. As a designer, this makes your life so much more easy. It can carry 5 times higher currents. So now this material, these electronics can withstand 3 times higher temperature. This is going to change the world. I will show you. It will exhibit 3 times higher thermal conductivity. And it will switch 10 times faster, which will do a lot of things, including making components and pieces of equipment much smaller. So you can see why, with this lineup of benefits here, why silicon-based devices have approached their material limits. So what are our peers saying? What are people in our industry saying about silicon carbide? The IEEE says silicon carbide is to the 21st century what silicon was to the 20th century. Well, this kind of sums it all up. The U.S. Department of Energy says that wide bandgap semiconductors, these new semiconductors, are a foundational technology that will transform multiple industries, resulting in billions of dollars of savings. Here it is. This is really why the whole thing's happening. People are going to save money. My favorite is the Oxford University Press. They say that silicon carbide technology is a disruptive technology that has changed the trajectory of future semiconductor innovations. Key word is disruptive. What does disruptive mean? Well, a technological innovation that creates a new market. This is what it is. It's a technological innovation that creates a new market and eventually disrupts an existing market and value network, displacing established market-leading firms, products, and alliances. This is a big word, and this is a big deal. All right. Now you know what the revolution is. Where is the revolution? Well, the answer is the revolution is all around us. For years, forever up here, traditional transmission systems, power generation, transmission, distribution, customers, case closed. Now we're going to get into a little bit of, we still got power stations, right? But we're seeing other forms of generation, wind, solar, right? We're seeing people taking this energy and storing it for future use. We're seeing factories and office buildings being called smart, right? We're seeing homes being called smart. What's this all about? The never-ending revolution of power electronics devices is inside the smart grid, right? Here we see a city with homes, and I'm going to introduce a new term on the next slide. Inside the smart grid, we're going to have little microgrids. This is our future. A smart grid is an electric grid with automation, communication, and IT systems that can monitor power flows from points of generation to points of consumption, even down to appliances in your home, and control the power flow or curtail the load to match generation in real time or near real time. This is all possible with the power electronics revolution going on. And here, I want to show you advances in power electronics control systems. They drive efficient and reliable electric grids, microgrids, right? Here's my definition of a microgrid. Distributed energy. There are solar panels, there are wind turbines, there are combined heat and power, there are generators that produce a self-sufficient energy system that serves a discrete location. Its features: a microgrid is local. You know, it could be a campus, could be a small town. A microgrid is independent. You know what that means? If the main grid goes away, the microgrid doesn't need the main grid to stay up and running. And a microgrid is intelligent. These are great times. Now, I want to single in on or focus on some of these little things I've been talking about. These facts will blow your mind. Do you know that the Earth receives more energy from the sun in 1 hour than is used in the entire world in 1 year? That's incredible. 0.3% of the Earth's land area covered in solar panels could supply all the world's electricity needs. And the cost that goes into creating solar panels is paid back through clean, renewable electricity production within anywhere from 1 to 2 years. So if you look at just this small microgrid and solar photovoltaic power, right? It's all done with light and light particles. Photon particles carry light energy from the sun, and they hit these silicon or silicon carbide solar panels, right? And what we do is we create there the flow of DC electricity. So DC is no good to us, so we have this inverter here, right? Here's an inverter, and an inverter converts DC, here we got conversion again, DC current to AC current that you use in your home. You charge batteries or put onto the grid. So here we see the makings, and I'm focusing in here on this inverter. this power electronics device loaded with either silicon or silicon carbide that we're loading, we're powering electric panels, we're storing energy in batteries. This is the future. Wind power, same story. Wind is a form of solar power created by the uneven heating of the Earth's surface. Prices for power contracts are as low as 2 cents per kilowatt hour. These prices are recorded by the U.S. Department of Energy. Again, wind turbine, inverter. Your inverter taking DC energy, DC your batteries, storing energy, and also supplying power to your house, your power grid, your electric car, whatever. Another part of the microgrid. Now, here's what else is happening with power electronics. The transformer, isn't it wonderful? It's got a primary, it's got a secondary, it's got a core, and this is the design for the transformer. We've been using it since 1882. Well, there are improvements that are on the way, that are here today, that have been limited due to heat and frequency constraints. The transformers of the future are all going to be solid state. They're all going to be components that I've been talking to you about that we're going to turn on and turn off. So we're going to have AC coming in, we're going to convert it to DC. So the DC now will be linked through a conversion system here at high frequency, either 10 kilohertz or 20 kilohertz, where we're going to go from DC to DC, from one DC level to another DC level, then switch back to AC, and this is all going to be done with power electronics in transformers. Here's another schematic of a solid state transformer coming in 3-phase, right? 1, 2, 3 phases. These are all devices that you turn on and turn off. We're going to go AC to DC, DC at 10 to 20 kilohertz. We're going to transform to another DC level and then create an AC output with another conversion, DC to AC. You can go 3-phase to single phase. You can go single phase to 3-phase, or 3-phase to single to 3. Transformers will be 1/10 the size they are today. Electric cars. This is all part of the silicon carbide revolution, electric cars. You see here we have a battery charger, a high voltage battery. You have, and this is all DC. You can take DC, convert it to AC for your ancillary loads. You have a bi-directional converter. This is all DC still. You're going to go through an inverter again that goes AC to DC to AC, DC to AC. Turning electric motors. You got torque to drive the wheels. Your Tesla. Your Model 3 Tesla has 24 silicon carbide MOSFET modules in each and every car. This represents almost 2 million silicon carbide MOSFETs on the road. This is happening today. So, all of these things that are going on, how is everything getting paid for? A revolution must have funding. Here is the source of the money right now. It's the U.S. Department of Energy. They've been behind this for a good 7-8 years, I'll tell you. And how they do that is that they have launched a company that's actually located on the campus of North Carolina State University in North Carolina called Power America. They're a manufacturing institute that's been designed to accelerate adoption of wide bandgap power electronics. The very things that I'm here talking to you about today. They're using a wide bandgap material instead of the normal bandgap that we've been using for 60 years. Power America addresses technology needs in the development of wide bandgap systems to enable U.S. manufacturing, job creation, and energy savings by U.S. industry. Their mission is to accelerate the commercialization of wide bandgap technology by trying to reduce cost of the silicon carbide or the gallium nitride or whatever the combination of wide bandgap materials is that you're using. Improve reliability, to demonstrate system insertion advantages, and to strengthen the power electronics ecosystem. So the government is behind us here. Supporting U.S. manufacturing is a priority of all Power America activities. This slide, I'm telling you, this is 2 years old. I still have it up here because it's so much is going on around the world. Industrial motors. Wide bandgap materials enable higher efficiency. Variable speed drives and pumps, fans, compressors, HVAC systems. Electronics, they're already at use in large high-efficiency data centers. Grid integration. Bandgap-based inverters can convert the DC electricity generated from solar, wind energy into AC electricity used in homes and businesses, reducing losses by 50%. I showed you examples of these two. Utility applications. Wide bandgap materials can reduce transformer size by a factor of 10 or more and accelerate development of high voltage DC power lines. Electric vehicles, just went over it, right? Battery recharging losses reduced by 66%. Reduce the size of the cooling system by 60%. They offer greater efficiency in converting AC to DC. This is because, I'm showing you this because it's a wide bandgap material that's making this possible. Military, wide bandgap semiconductors are used in high density power applications, satellites, high frequency radar. Geothermal, sensors can withstand the harsh, high pressure, high temperature environments of geothermal wells. And I'm going to highlight this as a special story. Wide bandgap materials are being used in circuit breakers, but you can't call them breakers anymore. They're switches that open in 700 nanoseconds. Say no more. Here we go into that topic specifically, the solid state breaker. It's part 4 of my presentation, where I'm going to give you 2 specific stories of what's happening inside the revolution. A company named Atom Power, they actually had a speaker in Kansas City last week at the 7x24 Midwest Conference. And Atom Power is a company in Charlotte, and they've built a solid state circuit breaker. And I'll say this, that there isn't a company that you can name that makes circuit breakers that hasn't tried to do this before. The reason it never happened is because we didn't have a material conducting electricity that can handle all of the characteristics that are present when you're trying to use solid state devices to conduct electricity. This wasn't possible until silicon carbide came along. So what we see here looks similar to a regular circuit breaker, but what we're also seeing is that it's solid state. And I'm going to show you that each of the 3 poles has a switch in it instead of contacts. So you have your line side on the left side and your load side on the right over here. I'm going to show you how this is safer than any molded case switch or breaker. It's intelligent, self-aware, and it's dynamic. So each one of the poles of a single pole or a 3-pole circuit breaker actually has a diode inside that you can turn on and off the electricity, right? So you're not going to have a contacts in there so that contacts, when they're closed and they're conducting electricity, when you open them up, you're creating an arc, and it's like hard to open them up, and the arc can be harmful, right? We're not going to be using contacts. It's a switch, and this is loaded not with silicon, but with silicon carbide because of its wide bandgap, right? And in a 3-pole solid-state circuit breaker, we have 3 of these switches. And because we're dealing with power electronic devices, we can control them. We can do things with them that you can't do with a regular circuit breaker. We can actually put some brains inside the breaker itself. So you're looking at a panel board here with 15 amp, 40 amp, 100 amp circuit switches in here. You can actually digitally remote control these switches, these breakers. Unlimited amount of operations, because we're not putting any stress and strain on the components that are proper to a circuit breaker. And you have a dynamic time current curve. Now, normally I have a video that I could click on and the door opens and the creator of the panel and the switches talks a little bit, but trying it, a half hour before we started the program here at 3:30, it didn't work. So I'm going to tell you a little bit about what happens in there, right? You can go in to the software inside this panel and you can see all of the different circuit switches, right? And suppose this 40 amp becomes too small and you need an 80 amp. Well, you just go in and you change it digitally in the software here from 40 amps. You see the 40 over here, and you just slide the radio button to the right until you get to 80. Now it's going to ask you, is the cables that you got out there, did you put cables in that are large enough to conduct 80 amps instead of 40 amps? And it won't let you do it unless you say, yes, I have. So you can change the amperage. You can change the name of the breaker anytime you want, right? And incredible as this sounds, you can change the time current curve of each one of these breakers to coordinate with something upstream. In your data center, if you had all these circuit switches, you could selectively coordinate or selective trip coordinate the whole data center from your software. Incredible. So these are the things that you would have seen in the video. Now, as far as speed, the device, because it opens so fast, it's got a 3 microsecond round trip fault detection, which means that it opens 16,000 times faster than a regular circuit breaker, which means that your 100 amp circuit switch opens in 700 nanoseconds. And the 1200 amp circuit switch opens in 2 microseconds. Now, I haven't used the word millisecond at all. For everybody who knows what 16 milliseconds is a cycle, I'm saying not milli, but microseconds. Now, do you know what this does to arc flash energy? It gets reduced by 30, it becomes insignificant. Insignificant. Now, the reason this is all possible, of course, is because we're using silicon carbide in these electronic devices, and it gives it magical powers. But here's another aspect of what you can do with these fast-acting circuit switches. And you could actually put 1200 amp circuit breaker circuit switches on each side, and you created your own static transfer switch, going from one side to the other in 80 microseconds transfer time. So that's a whole another topic that is, or a whole other industry that's in the process of being built and formed right now. So to summarize, these solid-state breakers: arc flash mitigation, ultra-fast circuit protection, 3 microsecond round-trip fault detection, 100,000, I think it's higher than that. I think it's up to 200 KAIC, interrupting capacity. This is an old slide. I picked that up in my when I heard the Atom Power guy talk last week. So they're up to 200 KAIC. Remote dynamic time current curve adjustment. You can, fully selective trip coordination at your fingertips, surge protection, thermal memory, remote firmware update capability, easily networked. Okay. The second story, and it has to do with the company I work for. This is how I got so involved with silicon carbide. A silicon carbide UPS. So how does a UPS generate reliable power? Well, by putting semiconductor devices inside. You're going to take AC coming in, right? And you're going to convert it to DC, create a DC bus here so you can put batteries on. But then you're going to recreate the sine wave with that inverter. You're going to go DC to AC, and you're going to get the best output that's possible by using a silicon carbide material instead of the silicon. So the better the semiconductor and semiconductor device, the better the output waveform, right? So I'm going to briefly tell you how these semiconductor devices work and generate electricity, because we actually learned it earlier in the seminar, maybe 20 minutes ago. So we're going to pulse electricity and then create and sensing will tell us, hey, you've got enough electricity, we need no electricity. You're going to turn it on, turn it off, pulse, no pulse, pulse, no pulse, until we get the best output sine wave we can. That's how it works, right? We're going to control the semiconductor device on and off flow electricity. So here's the IGBT, an insulated gate bipolar transistor, all used in UPSs. And here's the inside of it. It looks, the schematic. It's got what's called a PN junction that I want to focus your attention on. PN junction means positive is the P and negative is the N, right? And there's a boundary. So we're going to store a lot of positive particles on one side of this depletion area inside this semiconductor, this IGBT, and on the other side we're going to have negative particles. So you know that positives and negatives attract from our physics seminar a little earlier in this program. So the PN junction's a boundary between P and N particles, right? So what we're going to do here, and we have this dividing line. This is like a no man's land that I talked about earlier. It's like it's a band gap. We've got P's and N's that want to be together, right? So we're going to add some more different materials to the P's and to the N's. It's called doping. This is going to make them very easy to conduct electricity by doping them up. So we're going to take a voltage. We're going to take power. We need energy to get those electrons into the conduction band, right? So we're going to have a positive and a negative. We're going to have a forward bias and turn it on, and look what happens. When we turn the voltage on, the depletion area goes away, and if there's no band gap to get across, bang, we have the flow of electricity. We now have started to conduct electricity through our semiconductor device, through our power electronics device. But now we get a signal that says, hey, you got too much electricity, turn it off, turn it off. So the easiest way to do it, where they did it years ago this way, they created a negative bias or a reverse bias. Instead of positive, it's negative. Instead of negative, it's positive. And the reverse bias, lo and behold, makes that gap so wide that electricity can't flow at all. So we have actually turned off our semiconductor device. That's how simple it is, but it's really not simple to design and make them. But that's what goes on inside your semiconductor device. So using silicon carbide, a wide bandgap material, enables the UPS semiconductor to exceed the limitations of silicon. This is inside a UPS, right? Inside of a UPS. And here's a quick note for all you electronics or fans or engineers out there. We're going to bring back the MOSFET. We're not going to use IGBT. So silicon carbide permits manufacturers to replace slow silicon bipolar transistors with single carrier or unipolar devices, not bipolar, unipolar devices called MOSFETs. They can be switched quickly, far more efficiently, These faster devices have the added benefit of more compact, less expensive packaging because they require smaller control circuitry. So the equipment shrinks in size, power density increases, and MOSFETs instead of IGBTs, well, the new semiconductor of choice is the MOSFET. It's unipolar. That's half as many actions that go on. It's smaller, it's faster, it's more efficient. It's a no-brainer. Say hello to the MOSFET again. So using silicon carbide in UPSs, we're going to see higher efficiencies, less heat rejection, less cooling, smaller footprint. Efficiency. Efficiencies using silicon instead of silicon carbide. On the left here, you have switching losses turning on the device, switching losses turning off the device, conduction losses. Well, using silicon carbide, you're conducting for the same amount of time, so the conduction losses are the same, but switching it on and off, we're going to lose or have a reduction in power losses by 73%. And there's much less, you only need 1/10 the material. This is why these switching losses are so dynamic, so large, right? Increases efficiency. So at 500 and 750 kW, from almost 20% load all the way to 100% load, we have in excess or higher than 98% efficiency. And I was able to use this actual test material that we got from a phone company where, let's see, here we go, where the actual test data itself in the lab was in excess of 99%. So we were getting high 98, low 99% efficiency, double conversion at the UPS. Heat rejection. Because there's only 1/10 the material needed. Silicon needs X amount, only 1/10 amount with silicon carbide. So thinner devices are faster and boast less resistance, less heat, etc. We're going to get at 75% load, 50% less heat. 100% load, 40% less heat. Your air conditioning bill goes down and the requirement for air conditioning devices goes down. Footprint. Because you only need 1/10 of the material, faster devices have the added benefit of more compact, less expensive packaging because they require smaller control circuitry, heat sinks, inverters, and filters. So you get immediately an average of 35% reduction in UPS footprint by going to silicon carbide. That's it. So the company I was talking about is Verizon. They put silicon carbide in a lot of their sites, and this at site 8 here, this was a transformerless UPS that was replaced with silicon, that was replaced with silicon carbide, and you saw a 2.2% increase in efficiency overall at this site. And this is years ago, 2-3 years ago. And they were able to bring to their upper management showing how they actually saved money by using silicon carbide and what the annual savings would be. So that is the end of the story, and I think I brought it in on time, and I have a couple of minutes for questions.
I do. Thank you, Anthony. I do have a couple questions. Let me ask the first one, and I think I hope everybody's on the chat or can see the chat. Robert had responded to Gabe Andrews, first of all, about kind of where this is being used. The first question, and Anthony, if you would please, what is the adoption been for smart circuit breakers or circuit switches? What has been the input from installing electricians and operators to any movement towards smart breakers or switches? And finally, does smart switches add any ability to reduce the switchboard footprint? It sounds like it does.
Well, yeah, this is something that I'm not up to speed on all these things that are going on. You would have to visit. There's only one company that's doing this. And all of the other circuit breaker companies, 4 of the 5 major circuit breaker companies in the United States have invested in this company too. But you were talking about the adoption of using this, and what does it mean to installers? Was that part of the question?
Yeah, well, and I would even go a little further and ask the question, where is NFPA on this? Where are the code officials? Because we're talking about going from a standard circuit breaker, the circuit breakers we've traditionally used.
Right.
Where are they at with solid state circuit breakers, circuit switches?
Okay, well, it's pretty basic here, because what we're talking about and what NFPA 70E talks about is the calculation of arc flash energy.
Yeah.
And if you go and look at the formula for how you calculate arc flash energy, it's all dependent on the time it takes to open the device.
Right.
So if you're opening in 700 nanoseconds, you're not going to have to put on any protective clothing at all, because the number is going to be so low.
Sure, and that's 70E, but when we talk about 70, where in the current code or where in the future code, and Doug, you might know this better than I would, I'm sure you do, but where in the current code does it say you can use a semiconductor instead of a metal-to-metal circuit breaker? In other words, who said it? Is there a UL listing for these things?
Yes, there is, and I'm amazed. It took UL forever, and I did a presentation with the CEO of Atom Power when I found out about their company, and brought him into the presentation that we did the first time, called the Silicon Carbide Revolution. He actually was able to do his portion by himself, but I was asking him, what are you doing with UL? There's nothing that really deals with what you have here. So it took forever for them to get UL listing. And the guy I heard last week mentioned that it's UL 489I. Now, I haven't ever seen that. I don't know what's in there, but UL had a heck of a time in figuring out how to test this solid state breaker.
I can well imagine why they would take so long, just because this is something that's so far out of their knowledge zone. And then again, and Jim Svoboda asks the question, how come we haven't heard about silicon carbide before?
Well, it's amazing that we haven't, because, well, I know that my company, Mitsubishi, has been working on silicon carbide and using it as a conductor of electricity for 14 years. And the only reason that we've seen it from them in the last 3 years is cost. It actually drives the cost of the product through the roof, and no one would pay that much money to buy it. But now it's gotten down to where when you're looking at the smaller wafers, this 2 millimeter, the 4 millimeter, or the centimeter wafers, we're about to go up to the 6 centimeter wafer, which would take us into maybe a megawatt of power. But again, it's the cost that's been doing that. And I'll say this too, if you want to look all this up, there is a natural form of silicon carbide on our planet. It's called carborundum. Carborundum. It's natural, but most of the silicon carbide that we're seeing going into these power electronics devices is baked. It's 1 atom of silicon to 1 atom of carbon.
Mm-hmm. Yeah, well, I mean, carborundum has basically been used for years as an abrasive.
Yes. Yes.
Okay. It sounds like no one else has any questions. So, Anthony, thank you very much for your time today. We appreciate it. And
thank you, Bill. Thank you, everyone.
Yep, thank you. And we'll start moving our way over to the next presenter. Doug, if you would.
All right. Can you hear me, Bill?
I can.
Good. Thank you very much, Anthony. It's very much appreciated. The next on our list here is Jim Martin with the Global Connectivity and Project Manager from Eaton. And just as a short introduction, imagine for a minute that everything's connected to everything and everything's remote. For example, all 20 some odd of us now are remote from one another, and yet we're controlling a meeting. If you convert that to the notion of a microgrid, or convert that to the notion of a dam that's being power operated, it's entirely conceivable that some aspects of that operation are remote. And that leads to the question about, well, who's controlling things? That leads to the question about cybersecurity. And I think, James, that's your lead in.
Yeah, thank you very much. That was a great lead in. Looks like I've got a very tough act to follow, so I will try to wow you. But yeah, what I'd like to do is I'm going to share my screen. I've got some slides. I'd like to kind of talk about this idea of business continuity. One, we talk about reliable power, but we also need to think about other ways that we can stop the business. So I'm going to talk about cybersecurity and defense and try to blend the two topics together. I went a little crazy with the slides, so we're going to go fast, but I was hoping that we would have, there would be something for you to refer to later. So the slides will be shared with you afterwards. Real quickly, when we talk about cybersecurity or information security, there are three major topics here that you have to think about when you're securing your system. One is availability. Can you get to your data, and can the right people get to your data? Two is the integrity. Is this data what it's supposed to be? Has it been changed, due to an accident, or has it been changed due to a malicious intent? And confidentiality, which means, is your data private, or is it going to end up, on a network? Is your intellectual property or our personal information going to end up publicly available? And what was mentioned was kind of everything being connected. Eaton Power Quality makes a wide variety of uninterruptible power supplies and other power distribution products, and all of them, with the use of the Eaton Network M2 card, can be turned into enterprise level IoT devices. So you plug this card in, all of a sudden you have a smart device that is part of this connected world, part of this smart grid, this microgrid, etc. Let's talk about a few of the things that we've done, to really secure these devices. Since one, we've kind of made them, and it's not just Eaton, but I think the world is making devices much more accessible and much more manageable. But we're also, by connecting them, we are putting them at risk, putting ourselves at risk. So here are some of the things that we've done to secure this device. On the level of encryption, we ensure that every firmware release uses only the latest encryption algorithms. We only enable secure or encrypted protocols, and the firmware file itself is encrypted, so it cannot be evaluated by any malicious actors. In the realm of authentication and authorization, we support full role-based access control. We conform to California Senate Bill 327, so that you are forced to change that admin default password to something that responds to your organization's password complexity requirements. So you can say it has to be 10 characters, it has to have a digit, it has to have 2 symbols or 2 uppercase letters. You can also enable account expiration. So an account is only good for a certain period of time, as well as account locking. If you have logged in, failed to log in successfully 3 times, or 4 times, that's completely configurable, and it will lock out that particular account. And we do support digital certificates, X.509 public key infrastructure, so that you can ensure that not only is transmission of data encrypted and secured, but that the identity of the device or individual that you're communicating with. And Eaton's Cybersecurity Center of Excellence really has oversight over the design of all of its products now. So Eaton does cybersecure by design. Only necessary services are enabled by default. All of the component libraries that make up our firmware are evaluated by black duck analysis. Our file system is cryptographically signed so that any unauthorized changes to the file system are detected. And the firmware is also cryptographically signed so that we can control, and make sure that only authorized versions of that firmware are able to be installed on the network card. And we've kind of taken regular factory reset and we've upgraded it to a full data sanitization procedure. So again, these in a way, are I think for some people might say over-engineered, but we did a lot of this to get UL and IEC certifications, UL 2900-1 and the IEC 62443-2-2 cybersecurity certifications. But all of that really doesn't mean anything if an attacker is able to insert malicious code at a higher level in the supply chain. So we've done some things to mitigate a supply chain attack like what has been seen with SolarWinds. We have a independent code review process, and we're kind of at that great at a good size so that we don't need necessarily to rely on automatic code commits. So every single merge, every single push and pull on our code base repository has to be approved by 2 real people who do an independent code review of each other's work. That way, it's going to be very challenging for a malicious actor to kind of secretly get in there and insert a vulnerability into our code base. So again, to support the information security triad, once we have that code committed and compiled, we sign it so it can't be corrupted. We encrypt it for confidentiality, and we sign the file system to make sure that that data integrity is unchanged. So that and really the history and the events that are recorded by the card are always going to be true. At a higher level, in the idea of cyber defense in depth, I wanted to talk about some more general ideas and best practices for an IT organization or any organization that deals with data, smart loads, let's say. So encrypting your data, if you have the opportunity to encrypt your data at any level, it's very important, because what we're seeing now is that if an attacker is able to get a hold of your data, their main objective is to get you to pay a ransom. So the ransomware has become incredibly pervasive and insidious. And one of the ways that they get you to pay the ransom is they threaten to take your data and make it public. So in fact, they'll most likely release a piece of your data or a slice of your data to prove that they actually have it. So by encrypting your data, you're protecting the integrity of that data and the confidentiality of that data. Updating your systems. And really, this is kind of it's still a secondary causation, but it's one of the most common causes of being of a vulnerability that has been taken advantage of in the real world, is when they look at what happened, when they do the after action analysis, they look at the vulnerabilities. And these are not vulnerabilities that no one knows about. These are not vulnerabilities that have just been released. These are vulnerabilities that have been around for at least a year, but they have not been patched yet. So whatever kinds of systems you're running, whether it's an UPS network card, whether it's an operating system, whether it's an application, make sure that you're always patching and updating those to the latest versions. It will eliminate a vast majority of vulnerabilities that are out there. Have a data replication strategy. Make sure that you have a backup so that if you are the victim of a ransomware attack, or for some reason you have a catastrophic failure, that you have not lost your data. As attackers get more sophisticated, the dwell time of this data or the dwell time of the attack is increasing. Attackers may be in your system for a day, 3 days, a week, 2 weeks, learning about your system. So it's important to have a replication strategy that is isolated from your main system, so that for attackers that have a shorter dwell time, they don't even know that you have a backup. And this is probably the most important one, is educate your staff. Just today, I got an email telling me there was an error with my payroll, and that they had, and it looked very official. However, it was a part of it was part of an educational program that my company does to try to trick us into clicking on things we shouldn't click on. So I hit the button that this is a phishing attack, and I was rewarded with a little pop-up saying, "Good job, you recognized it." These types of programs are pivotal in educating people on the kinds of what people are trying to take advantage of out there, and to recognize phishing emails and other social attacks, because that's really to get into the system. The social attack is the most common way to get in, and to take advantage of that system, the most common way is to use systems that have not been updated. Also, if you can, apply a digital certificate, right? An electronic document that proves the ownership of a public key. This really allows you to be very, very confident that the communication between your devices and your users is encrypted, and that authorized people and devices are using that. Real briefly, this man-in-the-middle attack can take advantage of communications that are not using digital certificates. The attacker is able to insert himself into the communication pathway between a client and a server. And he can spoof data. He can change the data in midstream. He can capture all of your passwords, everything, right? So using certificate management and actually applying a digital certificate so that you don't see this warning, not secure, will, one, allow you to have confidence in that communication, but two, if you have to click through this insecure warning every single time, it creates some really bad habits and really poor cybersecurity hygiene. Another thing, and again, these are links that are going to be in the slides for you later. I've got a lot of material specifically on ransomware and some strategies, general strategies to protect against ransomware, but also some things that we've actually worked with some small and medium businesses to create an air gap for their replicated data. To try to, we've actually worked with a small business that's been documented on our website, Grandeur Housing in Canada, and they had been the victim of a ransomware attack 3 times, and they had really independently found our intelligent power management software, and they were interested in using it to create this air gap and automate the process. So, they get full credit for coming up with the idea, but we were able to work with them and create a replication strategy that has really been allowed them to recover from these ransomware attacks very quickly. And so, again, thank you for having me. If you need any more information, eaton.com/cybersecurity is our center of excellence. Has a lot of materials that may help you, and they do also offer services in the realms of cybersecurity. But if you have any questions about cybersecurity or about power UPSs, power quality, network cards, feel free to reach out to me. Thank you.
Thank you, Jay. Let's see. Have any questions? One comment. I don't know what's going on. Try that again. Well, that's weird. Can you hear me, James? Or is it muffled?
I can hear you.
Okay, I'm just getting some funny feedback here. One comment, interesting timing with the current Colonial Pipeline ransomware attack. Thanks for the presentation. Yeah. I spent the good first part of 10 or 15 years of my first part of my career in IT and responsible for mid-range systems at a wireless company. I used to see as the internet started to become a thing, we started to have to be concerned. Before then, we were worried about people trying to crowd dial our modems. Not quite as obvious anymore, but it still happens. With that, Doug, if you want to go ahead and introduce our last presenters today. Doug, you might be muted.
Okay, is this better?
Yeah, much better.
Sorry, I heard the feedback, so I decided to get myself out of the loop in case this was the problem. Chris Barton is on an airplane this afternoon. Chris Blazevich from NC Power will be covering the couple of their topics. NC Power is Caterpillar has spent a great deal, of time and effort aligning their capabilities regarding data centers. We'll hear partly about that today, and we'll hear a little bit about the hydrogen fuel generation. So, Chris, if you will, the floor is yours.
Great. Let me share my screen here. If anybody has questions as we're going through this, feel free to scan the QR code at the bottom right-hand corner there. That will allow you to submit questions and go ahead and put in some interests that you might have, if you have any, as we're going through this today.
Chris, as we go through this, if anybody has any questions, we ask them to use the chat, and of course they can follow up with you later.
Okay, perfect. NC Power Systems started out as a Caterpillar dealer in 1926. Became the Western Washington that was up in Alaska in the Yukon territories. In 1957, they moved down to Western Washington. And then in the 80s, they moved into Central Washington, acquiring that area. And in 1994, the Harnish Group ended up buying NC Machinery and Power Systems and merged that all together. Our focus is on risk management. With our project engineers, we have a very extensive management group for helping out engineering and designing all your project needs. As we move through, going through and doing simple installations, working with you to get the required data, if that's all that you're looking for, all the way up to doing a more complex and installation. We have many locations in Washington, Mount Vernon ranging from up north down to Chehalis down south, covering our eastern side in Wenatchee and Yakima. And we have resident technicians that are specializing in the data center coverage to help get those up and going faster. And anytime you have downtime, that's critical. Going back to our full feature of engineering product support, we're able to supply not only just the generator and the base tank and an enclosure, but we can also work with you to get that onto the roof of your building and do general contracting and engineering and all the way through for the full installation. In 1980, our 3500 platform was designed by Caterpillar, and it was at 75 kilowatts per cylinder. As you look at it now, as it grew, not only did it grow in power, but also meeting the new emissions tiers as they came through in 1996 and on up to Tier 4 where we're at today. We're also up to 200 kW per cylinder from 75 kilowatts back in the early days. That power density comes from a lot of different engineering design changes in the product, from the connecting rods to the pistons to the fuel systems. The 3516E standby and mission critical gen sets are rated at 3 megawatts now. So with that size of a unit at 78 liters of displacement, they have a charged air cooler. We are able to meet the NFPA 110 spec for a 10-second start time for hospitals. And the fuel system, the MEUIC fuel system, it's not like a common rail fuel system like what all of the competition has that are Tier 4. What we're seeing with that is it's a unit injector making high pressure fuel at the injector. So you're not running it all through the system and having a single point of failure with your high pressure fuel system. Performance is also ISO 8528-5 G3 load acceptance, accepts 100% block loading in one step, and 100% for ISO 8528-5 G2 in 2 steps. With the increase in power density, it allows us to go in and design a smaller package. With this smaller package, there's lots of cost savings that go along with that. Not only in the material costs that go into building the enclosures and packaging the units, but also in the shipping of the units. You know, you can get it down in size so that you're not on a super load going down the freeway as you're going to delivery, which can decrease your costs and cranings that go along with that for offloading. Cat Connect is another way to monitor your units. Cat RAM, it's the remote asset monitoring system that Cat offers that allows you to use it through your laptop, your mobile app on your phone, and be able to go in and look at what's going on. Make sure that your block heaters are warm, your condensation heaters are good, your batteries are charged up and ready to go at a moment's notice, as opposed to having to go out and periodically check through these things or waiting for an alarm to go off. And it will notify you if something does go wrong. We can also gather the data for emissions reporting, run times, percent loads, fuel burn for your reporting. Makes it a lot easier for keeping everything up to date. Product security, we can go through and integrate many different systems into our security and go through multiple firewalls, whether it's the customer firewall or Caterpillar's firewall. And if you have any questions about that, we're happy to get our security team, Caterpillar security team involved, and they can work with your security team to make sure that your data is secure and not getting out to anybody it's not supposed to. Next, I got Rick Walkup, and he'll talk about the hydrogen-based system.
Yeah, I'm unmuted. Can everyone hear me?
Yep.
Great.
Yep, you're
Yeah.
good to go.
We were trying to choose an additional topic to finish this off today, and we chose hydrogen, which has been talked about a lot in the news as a potential energy source for the future, a new fuel. So it's titled Hydrogen-Based Caterpillar Power Generation Solutions. So my name is Rick Walkup. I'm the territory manager, or was the territory manager. Now I'm a data center account manager for a lot of data centers kind of mid-tier west of the Mississippi. And I'm situated, as you can see behind me, in the Palm Tree region of Phoenix. So I'm going to start out with a little bit of why. Why is hydrogen an interesting fuel for the future? And it's pretty down the what you'd expect, that it's more of a green fuel. Customers have sustainability goals that they want to meet today to reduce greenhouse gases and reduce emissions. Investors in these companies are expecting their investments to have environment, social, corporate governance progress. Governments are trying to keep everyone healthy in a safe, non-climate changing planet. And then lastly, why hydrogen is that it kind of solves a problem with renewables with the supply and demand mismatch. And we'll get into that in the next slide there. When it comes to, and I think this is just an example of a solar array. When it comes to a solar array, you imagine you put it in your roof, and if you're not consuming the power for your house and you're not storing it, because most of them don't have storage, then you're putting it back in the grid, and that's great because those solar panels are fully utilized. But the problem you run into on large scale is that, if you're powering California with 60%, 70% solar, there's going to be times when you have excess. And what do you do with it? You turn them off and not utilize them? Or do you do something else with them that you could store for future use? And what you can do is you can extract hydrogen out of water and store it. So getting to the next slide. Today, there's, the vast majority of hydrogen in the market is what they call gray hydrogen. And it's no better for greenhouse gases than using natural gas. It's the next step to be more environmentally friendly is what they refer to as blue hydrogen, and there's various grades of that. But to generalize it for today's short presentation, is that they're scrubbing it and they're creating it from natural gas, and it's better. But the future and what they're really talking about in the news and for the long term is green hydrogen, and that's made, like I said, with renewable energies, excess renewable energies using electrolyzers. The problem comes is that it's very expensive. So the question is, well, when does this technology may come into the mainstay? And I found these charts very interesting. Starting the bottom right, really, and that from the worldwide view of added power generation back in 2012 to 2017 was 50-50 fossil fuels versus renewables. 2017 to 2022 current, we transferred to 75% renewables, and moving forward, that's just going to become greater and greater. They projected 82% up to 2027, and I'm sure they're projecting in the 90s after that. So you can see in the top right, those charts show the CO2 per, I think it's megajoule, and the trend starts to go negative. That We're not emitting CO2. We're not burning CO2 to make electricity. The consumption worldwide is expected to double by 2050. And as we shift to these renewables, we're going to have a lot of excess. So what are we going to do with it is the question. Currently, you know, the issues really are, the pace setters really are safety, scale, and policy. Safety is, and I didn't include these slides because of the limited time, is the fact that it's more of an invisible gas, and there's this thing called hydrogen embrittlement that we could get into. Scale is the infrastructure, that the molecules are smaller and they'll leak out of that natural gas pipelines at a higher rate than natural gas. And storage and transportation is very, very expensive, and you have to follow the safety procedures. And then policy, that's your investment from our government to make it all happen. So the reality is in the next page there, Chris, is that currently, and in Europe they're doing this, you can look it up, they're blending hydrogen into natural gas pipelines. Considered up to 20% hydrogen can be safe. It's not going to make your flame on your stove invisible. It's not going to cause significant leaks that are going to be an issue, and it's going to avoid hydrogen embrittlement problems. So most engines aren't going to really run all that different. Hydrogen is a lower volume or lower power density fuel, so you're not going to be able to make as much power in your gas generator, but ultimately you can use the same products that we have available today. The future, and we don't know when that might come, if it will come, is moving to 100% renewable fuel, which would be 100% hydrogen. And it is going to require specialized gensets and specialized infrastructure and transportation. It will be higher cost at first, but hopefully it comes down. So just a little bit more experience from Caterpillar's side here is that we've really been running high concentrations of hydrogen for up to 20 plus years. Certain applications for industrial applications, coke oven gas and wood chip gasification run up to 60% hydrogen. And they're very, very large engines with low power density. It's just not as power dense, and you're never going to wear this engine out. Like a diesel engine could be very power dense, gas engines really can't. So most of our product can run 10% all day long. Half of the other ones can run 20%, no big deal. And we've seen no real impact to maintenance issues, maintenance schedules, durability, reliability. It's not a big deal. So we're going to continue to do research, because when you get up in the higher concentrations, things do get tricky. But we'll just give you a little look here of our gas product lines. These are products made out of Mannheim, Germany, Kiel, Germany, and Lafayette. The G3500, you'd probably recognize that 3500 for the data center industry. So just to look at that one example, honestly, when you're looking at gas engines and you're looking at experience with hydrogen, you're probably going to use them in an industrial site, and our product out of Germany is more tailored towards those industrial type applications. So you see higher numbers on those products, but just to take a look at the product that we gasified that operates in data centers, we have experience running up to 40% hydrogen, and we were comfortable over 5%. And I'm sure that will move to 10 or 20 soon. So just to sum it up, renewable hydrogen may be an energy of the future. Customers are interested in it, and Caterpillar offers product capable of running it today, 10, 20% blends. Large amounts and high concentrations of hydrogen won't be easy. They will take some time to develop. The industry is very interested in it, and Caterpillar is actually ramping up, and will continue to look at hydrogen as long as it appears to be a viable fuel for the future. Oh, 5:01, I missed it by a minute. So if there's any questions.
Does anybody have any questions? If so, go ahead and bring them up on the chat. Hearing none.
You suggested hydrogen was expensive. Curious if that's because of the electrolyzers or for some other reason that we're not seeing.
It's mostly transportation. The electrolyzers are expensive, but they're the items that will be coming down. It's the transportation and moving this fuel around that seems to be the long-term cost.
Okay.
Rick, do you want to take that one about the diesel free by 2030
I don't see it. Oh, there it is.
on the chat?
How does CAT responded to data centers stating that they will be diesel free by 2030? And I think those are the largest data centers. I recalled, one of those, Microsoft, it was public, having a carbon neutral footprint. I don't know that it was, I think it was offsetting carbon emissions, but yeah, I think they'll find a way. It's a matter of time. It's very interesting how that they're running standby and they still want to replace those with something else. 2030 is probably very aggressive, and they're probably going to keep the assets they already own.
And I'm assuming the storage issue is with the hydrogen. If you were to look up the hydrogen tank and compare it to like a diesel tank, I don't know the size difference, but we're talking like 100 times larger. They're just monsters that you will see them next to the data center. You can't hide them. They're so large. If you're looking at it for like 48 hours. So it's this cost of the tanks and the technology of the tanks. They're monsters.
Well, I mean, essentially, you've got to keep the hydrogen in a liquefied form, which means you've got to continue to keep it insulated.
And that's the other option, yeah.
And, otherwise you basically have got highly compressed hydrogen. Now, has anybody asked, I'm sorry, I dropped off for just a second. Has anybody talked or brought up Microsoft and their plans to supposedly, go to hydrogen-based fuel cells?
Yeah.
And where have you heard anything about that, or is there any movement? Again, we've heard a little bit from Microsoft in one of our previous meetings, but what are you guys looking at this point?
I know as far as Caterpillar goes, back in, what was it, early 2000s, down at the wastewater treatment facility here, we had a fuel cell that was running off of the methane going down there. As far as hydrogen, I'm not sure where they're going with the hydrogen fuel cell.
Okay.
Yeah, I don't see Caterpillar getting involved. We would maybe partner in that industry, but I wouldn't see us making those. We are involved with that project, though, in a different manner.
Okay. Let's see, I'm just catching up with other questions. So you answered the one about data centers saying they'll be diesel generator free by 2030. Did you get that one already? How does CAT respond to data centers stating that they will be diesel generator free by 2030?
Yes.
Yeah. I think that they will go diesel generator free in certain states and certain industries, but I don't know about 2030,
Well, we're talking specifically about data centers, and it's again, this goes back to our friends at Microsoft and other large hyperscalers that have said we're going to be carbon neutral, or we're going to be carbon negative even by 2030.
There's plenty of ways to go carbon neutral by offsetting and buying credits and other strategies. I heard that that's on pause, but that was part of their strategy.
Okay. And then green H2, dollars and electricity, or electricity and PEM membranes. David, I'm not quite sure what you're asking there. But And then the question is, the comment is, there's subsurface solutions internationally that are more cost effective for large H2 storage, 50 to 500 ton range. But
Okay.
that sounds like that's possibly, not where you guys are focused.
Subsurface solutions.
Well, it probably would be, I'm guessing, David, you can confirm this, that they're talking about injection wells where you pump high pressure
Yeah.
hydrogen into, maybe existing.
Just like natural gas wells, yeah.
Yeah. Mm-hmm. And once
Yeah,
you've
then
depleted,
you still need a pipeline to get it to your data center or storage at the data center. I think it's storage at the data center or the pipeline that would be the real hurdle. They're usually not out in the middle of nowhere.
well, some of them are starting to become out in the middle of nowhere.
Yeah, you got some up there.
I've seen a few. Well, I've seen a few all over the U.S. and in Europe and in South America that were out in the middle of nowhere. So but you're right. A lot of them are not. They're in major metropolitan areas, and yeah.
So if anyone wants more information or to talk to a subject matter expert at Caterpillar, please reach out. That QR code, or you can get my email from any of the hosts, Jim or Bill.
Yep. Let us know, and I think Jim will be posting some information and the presentations that have been provided, and we'll also post the video. I believe, Jim, are you still on there?
I am, Bill, and yes, when you get the video over to me, I'll get it up as well as the copies of the presentations.
All right, as soon as I get Microsoft Outlook to work. And otherwise, thank you, gentlemen. Thank you.
Thank you.
We appreciate the time. Thank you.
Thank you, everyone.
I think the only other thing we really wanted to have a discussion, and there's still a bunch of people online, so thank you for sticking around to the meeting. And I think we're looking for feedback. Doug, you can correct me if I'm wrong, but we're thinking about what does it look like if we decide to have an in-person meeting in September, and what is the comfort level of certainly our local members to attending such a meeting, or would we be better served to continue to have online meetings at least through the September timeframe, which would be our last meeting of the year, and then look again at this at the beginning of 2022. So,
hey, Bill, Lee Moss here real quick. I just want to pop in. We have our Oregon Southwest Washington chapter meeting in person this Thursday night at Top Golf for 2-3 hours. So I'll report back on that.
Yeah, please do. But I mean, that's what I saw when I got the invite. That was more of a meet and greet, not really a session. Is that correct?
Yeah, I'd agree with that.
Okay. So that's more of everybody going out and playing golf that likes to play golf, and you've got a limited attendance list.
Yeah, but it is indoor at Top Golf, so there are food and beverages provided, areas for networking in person with mask on, that sort of thing.
Okay. So does anybody here have a comment about, September and, where you might be? We're just trying to get, I guess we're just trying to get an idea of where people are feeling right now. And there is no wrong answer here, folks.
CPSI supports in person.
Okay, thank you. Anybody else want to,
Hey, Bill, check the chat. I see a few folks are chiming in on the chat in terms of how they feel about in-person meetings.
Yeah, I see that, Carrie. Thank you. Robert, I see you're not afraid of in-person. Outside in-person in September is a possible path. I had to look at that one twice too, because it started to look like a movie title.
Well, we've never done an outdoor meeting. I mean, hey, it's the first time for everything.
That's true. That's true. Okay. Eaton will support person likely. And again, probably what we would do is if we do it, regardless of what we do, well, maybe not. But if we do it in-person meeting, we'll probably continue to use the Teams platform so that people who either can't or don't feel comfortable being in person would still be able to continue to participate, and that's important to us. I don't think that at this point, unless people just stop using it completely, that we'll ever drop the Teams platform as an option. It's just become way too valuable, at least in my opinion. Anybody else? There's still a few people left on board. Does anybody else have any other comments they want to make? Thank you for those of you who have spoken either, vocally or by your fingertips on a keyboard. Hearing nothing further, Doug?
Enjoy the meeting this afternoon. Thank you all very much for attending, and we'll talk to you next time in September, one way or the other. Take care.
Thanks, everybody.